In this video, we're going to take a look at alternating series. So what do we mean by alternating? Well, we've actually seen a few alternating series previously, but let's set out the meaning of what alternating means. So here we have two infinite series. One of them is -1/2 to the nth power, and the other one is an infinite sum of -2 to the n plus 1th power. If I write out the first few terms of the -1/2 to the nth power summed up from n equals 1 to infinity, if I plug in n of 1, I get -1/2. If I plug in n of 2, I get a positive 1/4. If I plug in an n of 3, I get -1/8. If I plug in n of 4, I get a positive 1/16. The next one, when I plug in 5, would be a -1/32. The next one would be a positive 1/64. And we would keep doing this pattern where the denominators are all powers of 2, and we switch back and forth between, we can rewrite this as having a positive 1 on top versus a -1 on top. So in other words, we're flipping back and forth between positive and negative values. So each term goes from negative to positive. Every other term is negative and positive. The same thing would happen with -2 to the n plus 1th power, or the n plus 1 power. In this case, when I plug in a 1, I get -2 to the n plus 1. That gives me a positive 4 to start out with. And then I would get a -8. When I plug in 2, my power would be 3. When I plug in a 3, my power would be 4. So I'd get a positive 16. When I plug in the n equals 4, I would get an exponent of 5, so that would be a -32. And we just alternate back and forth between positive and negative numbers. Both of these series are alternating. In fact, both of these are geometrical series as well. So because R is in absolute value less than 1 up here, this series we know would converge, this first one. And since R is in absolute value bigger than 1, in this series we would have divergence. So we can have converging alternating series and diverging alternating series. But the concept of alternating is flipping back and forth between negatives and positives. So every other term is flipping back and forth between negatives and positives. Obviously, we would like a more formal definition than flipping back and forth between negatives and positives. So we do have that. We have a more formal definition of an alternating series. So it's not just enough to have a negative on the inside here. Basically, what I need to be able to do is I need to be able to write this series, do this way. As a positive component, all times -1 to the nth power. So I can factor out that -1, but remember the -1 is being raised to the nth power. So notice my series is a -1 to the nth power times this part, this 1/2 to the nth power, which is positive. I can do the same thing here, except obviously it's being raised to the n plus 1th power when I factor out the negative. And then I have a positive part, again, in this case, being raised to the n plus 1 power. You can also, if you want, multiply and make that look different as well. But the point is, with an alternating series, we have negative 1 to the n as a factor times a piece which is always positive, or negative 1 to the n plus 1 power as a factor times a piece that's always positive. That will give me terms which alternate back and forth between negative and positive numbers. So this is what we just did. We rewrote each series as negative 1 to the n times a positive part, or negative 1 to the n plus 1 times a positive part. And that's really the definition of alternating. An alternating series is a series that can be written as negative 1 to the n times terms which are all positive, or negative 1 to the n plus 1 times terms which are all positive, obviously summed up from 1 to infinity, or we can use different lower bounds if we'd like. So it's an infinite series where I can write it as negative 1 to the n, or negative 1 to the n plus 1 times positive terms. So these two series that we looked at, obviously were both alternating because I could do that. By the way, we saw earlier a sequence of numbers that was 2 plus negative 1 to the nth power. That is quantity 2 plus, in parentheses, negative 1 to the nth power. This negative 1 to the nth power cannot be factored out of the series. So this is actually not alternating because of the 2 plus. The terms of this series, we're going to do, when I plug in 1, I get a 1. When I plug in 2, I get a 3. We do go back and forth between 1 and 3, but notice that we're not going back and forth between a positive and a negative. So this one is not alternating. In other words, in order for it to be alternating, this negative 1 to the nth power has to be multiplied times the entire other part of the sequence, other part of the terms. Or negative 1 to the n plus 1 power has to be multiplied times the whole thing. I can't just have negative 1 to the n in one part. I have to be able to factor it out of the entire term, which I can't here. So I need to be able to factor that negative 1 to the nth out in order for it to be alternating. We are going to examine alternating series in this section, in this video. And they come up in a lot of places, but one really nice thing about the alternating series is that there is a really nice test for convergence if we have an alternating series. with the P series, with the integral test, we needed our functions to be of a certain type. With the limit comparison, we needed our functions to be of a certain type. With the alternating series, we also need our terms of our series to be of a certain type. We need those terms to be alternating. If we have an alternating series, whether it's -1 to the n times a sub n summed up, or -1 to the n plus 1 times a sub n summed up, then the alternating series converges if the following two conditions are met. The limit of the positive part of the alternating series is 0 as n goes to infinity, and the positive parts of our alternating series are decreasing. So if we have an alternating series, to check for convergence, we just need to find if the limit of the positive parts go to 0. And they decrease towards 0, basically. By the way, if the limit of these terms is not 0, then based on that divergence rule, the alternating series would diverge. So if the limit is not 0, then the series diverges. So this is a really, really nice test. Very efficient, very quick. When we have an alternating series. Let's do an example. Let's determine the convergence of this series using the alternating series test. Now, this infinite series is written in a very nice way. It's written with the -1 to the n already factored out. It's the infinite sum of -1 to the nth power times 1 over n. If I look at this, obviously the -1 to the n part I've already factored out. So we have an alternating series. The alternating series test says that if this positive component decreases, which it does, it is decreasing as n goes higher and higher. So it decreases and has limit equal to 0, then this series converges. Notice that the limit of 1 over n as n goes to infinity is in fact 0. We know that just based off of rules of limits. And we do know that it is also decreasing. 1 over n plus 1 is smaller than 1 over n. Technically less than or equal to, but there you are. So usually I don't write that second part. I just say, oh, it's decreasing. It's pretty clear that it's decreasing and the limit is 0. So by the alternating series test, this alternating series converges. So this alternating series converges. Now, here's the strange thing about that. What if this was not alternating? What if instead of taking the infinite sum, I took the infinite sum of the absolute value of every term? Well, if I did that, the absolute value of -1 to the n, that's just going to be 1. And the absolute value of 1 over n, since 1 over n is positive, that is going to be just 1 over n. So when I take an infinite series, and instead of adding up the alternating series terms, I take the absolute value of the alternating series terms, I get a sum of 1 over n. That thing diverges. So my alternating series converges, but if I would have just done the same thing but just had all positive terms, that alternating series would diverge. And by the way, I know this diverges because this is a p series where p is 1. So that's how I know that it diverges. 1 over n to the first power. So sometimes the alternating series will converge, but when I take the positive terms and add them all up, then it diverges. There are other times where the alternating series will converge, and then when I take the absolute value of the terms, it also converges. Like for instance, in our first example, we had -1/2 raised to the nth power summed up. Well, +1/2 raised to the nth power would have also converged. What we're getting at is the distinction between absolute and conditional convergence. In the previous section, when I looked at the ratio and root test, we talked about a series being absolutely convergent. And I said, yeah, that just means convergent. And I think I said it means convergent in a strong way. Well, now we're going to get to the definition of what that absolute convergence actually means. So first off, a series can do one of three things if it's alternating. It can diverge, so the series just diverges, and that's as with any series. It can be absolutely convergent, which means that the series converges, and also if I take the absolute value of the terms of the series and create a new series with that, that also converges. Or, like the example we just saw, it could be conditionally convergent, where the series itself converges, but if I take the absolute value of the terms and add those up, that would diverge. That's what we just saw, that the series converged, the alternating series converged, but if I wouldn't have had the condition of being alternating, then it would have diverged. That's why this is called the conditional convergence, because again, we really only get conditional convergence when we have alternating series, when we go back and forth between negatives and positives. If all of my terms are already positive, then the series is going to do the same thing. These are going to be identical. So in previous sections, we didn't talk a lot about absolute convergence because we were dealing with positive terms in our series for the most part. And the absolute value of those positive terms would be identical to the positive terms themselves. So really, this distinction between absolute and conditional convergence really is only a thing in alternating series, basically. There are some other places where it comes up, but alternating series are the main place where that distinction between absolute and conditional convergence comes up. Let's take a look at an example. Let's take this series, -1 to the nth power multiplied times n plus 1 divided by n. And we're going to start our infinite series at n equals 2 and go up to infinity. So this series is obviously alternating. I can factor out a -1 to the n. When I do that, I'm going to be left with n plus 1 over n. So I would take the limit of that part. In other words, I take the limit of n plus 1 over n as n goes to infinity. Obviously, that's 1, which is not 0. So that means this series diverges. Now, I don't need to check the absolute value thing because we know this diverges. If I did the absolute value of the terms in the series and sum those up, that would also diverge. By the way, again, what I was saying up here, since the series converged, but the absolute value terms when added up diverged, we would call the original series conditionally convergent. Another way to say that is that the series converges conditionally. So it's either is conditionally convergent or the series converges conditionally. That was my first series. Obviously, the one I just did in example 2 diverges, and then I'd stop there. Let's do another example. And on this series, we want to also determine if the series is divergent, if it's absolutely convergent, or if it's conditionally convergent. If you want to try this on your own, push pause on the video. So this is an alternating series. I could factor out a -1 to the n plus 1. So the first thing I do is I take the limit of what I call the positive component. That's what I get when I factor out an n -1 to the n plus 1. So the limit as n goes to infinity of 1 over n squared is obviously 0. So that means the series converges. So the series we know converges. Based on the alternating series test. Now we're going to determine whether that convergence is conditional or absolute. So what I would do is I would take a look at what would happen if I put absolute value bars around each term in my series. In that case, absolute value of n squared is just n squared. Absolute value of -1 to a power is just 1. Once again, this is a p series. In this case, p is 2. 2 is bigger than 1. Therefore, the infinite series I get when I put absolute values around each term of my alternating series also converges. Again, that's because we have a p series with p of 2. This means that my original series converged. The absolute value of the terms series also converged. And this is the case where we say, this means my original series, the one I've been dealing with, is absolutely convergent. So my original series, I know, is absolutely convergent. Not only does it converge, but the series I get when I take the absolute value of the terms also converges. These are the three types of convergence that we'll see. So if the series converges and the absolute value of the terms series converges, then we say it's absolute convergence. If the series diverges, then the series diverges. Series is divergent. If the series converges, but the absolute value series diverges, then that's called conditional convergence, or we say the series is conditionally convergent. So the example that we just did, we got absolutely convergent because both pieces converged. Let's do another. As always, if you want to try this on your own, you can pause the video. So we want to see if this infinite series is divergent, absolutely convergent, or conditionally convergent. It is alternating, so I can use the alternating series test, which just asks me to factor out the -1 to a power and ask, does the limit of the positive component as n goes to infinity go to 0? Does it decrease towards 0? Well, in this case, if I factor out the -1 to a power part, I end up with just a 1/5. That's not affected as n goes to infinity. That's actually has limit of 1/5. So by the alternating series test, what we're saying is that this infinite series diverges. And that's it. That's the whole thing. Alternating series test shows that it diverges. We can stop there. We don't need to do any absolute value of the terms work because we know the series diverges. So stop there and then move on to the next problem. So here is that next problem. Again, if you want to try this one on your own, go ahead and do that. Oh, limit here. So excuse me. So let's do this. Let's figure out whether this converges conditionally, converges absolutely, or diverges. So this is alternating. So the first thing I'm going to do is look at the alternating test. If I factor out a -1 to the n, I'm left with 1 over the natural log of n. Now I can put that in parentheses because n's always positive, and I usually put things in parentheses anyways. As n grows, natural log of n also grows. Therefore, 1 over the natural log of n is going to get closer and closer and closer to 0. So by the alternating series test, this series by itself, this alternating series, converges. Now, if I want to know whether that convergence is absolute or conditional, then I can put absolute values around each term in the series and see if the new series, the one with the absolute values, also converges. If I put absolute values, we know what's going to happen. -1 to the n is always going to be a 1 when I take an absolute value of that. It's either going to be -1 or 1. Absolute value of 1 is 1. Absolute value of -1 is 1. And since we're plugging in positive numbers into n, positive integers, I should say, into the natural log, notice I started with n equals 2 on my summation. That's because you don't want to put a natural log of 1 because natural log of 1 is 0. So basically, I'm getting natural log of n, okay? Those are always going to be positive numbers. So the absolute value of the natural log of n is always just the natural log of n. Now this thing, whoops, this thing diverges. One way to see that is by a direct comparison test. To the infinite series 1 over n. So if I do a direct comparison to 1 over n, 1 over n has smaller terms than 1 over natural log of n. I know this one diverges. And so the one with the smaller terms diverges. That means the one with the bigger terms also diverges. Another way to see that is just to realize that natural log of n is a really, really slow growth. So this fraction is going to go to 0 really, really slowly, a lot even more slowly than 1 over n. So what does this mean? Well, this means that my original infinite series, while it converges, if I take the series of the absolute value of the terms, that series diverges. So my original infinite series, we would say, converges conditionally. Or again, is conditionally convergent. It converges, but only on the condition that it is alternating. Let's try one more. Here we have an infinite series, which is summing up from n equals 1 to infinity, -1 to the n plus 1 power over n factorial. As always, if you want to try this on your own, push pause. This clearly is an alternating series. I can factor out a -1 to the n plus 1 power. If I do that, I'm left with a positive part of each term of 1 over n factorial. So since this is an alternating series, I'll use the alternating series test. Take the limit as n goes to infinity, we're going to get 0. And that means the infinite series itself converges. Now that I know the series itself converges, I want to see if that convergence is absolute or conditional. And so what I do is I take another infinite series, which is the infinite series of the absolute value of all of my terms. Absolute value of -1 to a power just becomes 1. In factorial, when I'm plugging in positive integers, is always positive. This infinite series we've seen before, it converges. And again, you would, if you had to show this, you'd use a direct comparison to something like an infinite series of 1 over n squared. Since n factorial grows a lot faster than 1 over n squared, these fractions are going to be smaller. And since we know that the infinite series, well, let me just write it down. Infinite series of 1 over n squared, that converges. And these terms are bigger than those terms, then by the direct comparison, we can say that this infinite series also converges. We did that one earlier, so in a different video, obviously. In the direct comparison video, that was the example. That all being said, now we see that the infinite series converges, and also when I take absolute value of the terms, that infinite series is also converging. So the infinite series, we say, is absolutely convergent. Or, in other words, it converges absolutely. So we've done a lot of work. Obviously, the alternating series test is a really nice test. It's pretty quick. All I have to do is make sure that the terms are decreasing and the limit is 0. I didn't stress a lot that these terms were decreasing. That's fairly self-evident. You have to come up with some really wild terms to have limit 0 but not be decreasing. So to be positive, have limit 0 and not decreasing. That's you get some kind of wild terms there. But the point is, the alternating series test is really nice, goes fairly quickly. That tells me convergence or divergence. If I want to also look at the series where I sum up the absolute value of the terms, that can tell me if my original series converges and the absolute value terms series converges, then we get absolutely convergent. We know our original series is absolutely convergent. And then conditionally convergent if my original series converged, but the absolute value of the terms series diverged. That would be conditionally convergent. And then the last option is if my original series diverged. So these are the three options for convergence of an alternating series. Both absolute and conditional convergence are indicating that the series is converging. Just how strongly it converges is the question. And then obviously the third option is divergent. Now, one of the benefits of alternating series is that alternating series have this really nice test for convergence. As long as the positive components of the terms are decreasing and limit is 0, then we're good to go. The other big benefit of alternating series is that we can approximate alternating series fairly easily. That is, if they converge, obviously. So if an alternating series converges, then we can do a pretty good job at approximating the sum using the first few terms, or the first maybe many terms. So what we're going to do is we're going to take an alternating series that I already know converges. In fact, this one we saw earlier converges absolutely. This -1 to a power n plus 1 divided by n squared, we know that that converges absolutely. So we're going to expand this series, and then what we're going to do is approximate the sum within 1 over 25 of the real value of the sum. In other words, I know it converges, so it's going to converge. This series is going to be converging towards some number. I want to get within 1/25th of whatever that number is. And then we'll say, well, what if we wanted to get within 1/50th of whatever that real number was? So let's start writing out, let's expand this series by writing out the first few terms of this series. So when I plug in a 1, I'm going to get 1 over 1. When I plug in a 2, I'm going to get -1 in the numerator and 4 in the denominator. When I plug in a 3, I'll get a +1 in the numerator and a 9 in the denominator. When I plug in a 4, I'm going to get a -1 in the numerator and a 16 in the denominator. So the numerators are bouncing back and forth between 1 and -1, and the denominators are the squares. Let's get a few other terms. The next term would be +1 over 25. The next term would be -1 over 36. The next term would be +1 over 49. And then the next term would be a -1 over 64. And then the next term would be a +1 over 81. And then the next term would be a -1 over 100. And it would go on and on like that forever. Let me make this a little bit smaller just for sake of writing it on a single line. Nope, that's not going to work. Well, then I'm going to make it this way. There we go. So the expansion of that series looks like this. Now remember, this series converges. So it converges to some value S. That means this infinite summation is some value which, again, traditionally we call S. So what if I want to approximate within 1/25th of S? I want to get a number that is within 1/25th of S. Basically what I do is I say, notice that this term, the fifth term, was 1 over 25. That means this entire component, well, let me explain this. This entire component, I can see because of the alternating nature and the decreasing nature, is going to be positive. The way I know that is that if I combined pairs like this, and I just keep doing that on and on and on forever, notice that because these terms are decreasing, when you combine the pairs like this is going to be positive, this is going to be positive, this is going to be positive, the next one will be positive, and so on and so forth. So I know that after I add up the first four terms, the remainder, we'll call this the remainder, is going to be positive. Now also, I claim that the remainder at most is 1 over 25. And the way I can see that is by adding up all of the terms except for this first one. This pair is going to add up to a negative value. This pair adds up to a negative value. Then the next pair will add up to a negative value. So this is going to be 1 over 25 plus a negative plus a negative plus a negative. In other words, it's going to be less than 1 over 25. So what I'm getting at is that the sum of the first four terms, which we again call our partial sum of S4, plus the remainder after the first four terms, is going to be equal to the actual sum. And I'm claiming that that remainder after the first four terms is positive. I'll say greater than or equal to, but we know it's greater than. And it's less than 1 over 25. So that means that the sum of the first four terms is within 1/25 of the actual summation for the series. So this infinite series, if I'm willing to approximate with 1 over 25 as my error value, is simply going to be the sum of the first four terms. Whatever that number is. Now, I'm going to punch that into my calculator. It gives me a crazy looking decimal of 0.7986, and that as a fraction is 115 over 144. Okay? So what I'm saying is that the number 115 over 144, or you can give the decimal version of that, let me write it this way, is within 1/25 of the actual summation. And that's because I know that this remainder when I put it this way, is somewhere between 0 and 1 over 25. Now, in general, that's what we're going to do. In general, we say, let's write out the terms. And if I want to approximate within 1/25th, I just wait till this term, this lead term on my remainder is 1 over 25. If I wanted to approximate within 1/50th, I'd wait till the lead term in my remainder is 1 over 50 or smaller. 1 over 49 is just a little bit bigger than 1 over 50, so I'd go to the next one and I'd do that. So let's just jump to that. We want to approximate within 1/50th of the actual sum. We know it adds up to something because we know it converges. And so I look at my terms. The first time that a fraction is under 150, we can't do 1 over 49 because that's a little bit bigger than 150. That's not within 1 over 50. So we go to the next term, which is negative 1 over 64, and we say, let's force that to be my remainder. So what is that? 1, 2, 3, 4, 5, 6, 7. That's the partial sum after 7 terms plus the remainder after 7 terms. And in this case, we have to look at it a slightly different way than we did with the 1 over 25. Because if I pair it this way, I can see that each pair is going to add to a negative number. So that means my remainder is going to be negative, but it's also going to be, when I pair it this way, it's going to be at the smallest negative 1 over 64, because it's negative 1 over 64 plus a positive part, plus a positive part, etc., etc. So basically, my remainder is going to be negative. It's going to be bigger than negative 1 over 64, but smaller than 0. And that means this 7th partial sum is within 1/50th of the S. And let's go ahead and add that. 1 over 1 minus a 4th plus a 9th minus a 16th plus 1 over 25 minus 1 over 36 plus 1 over 49. That becomes, again, a really ugly decimal. I'll write it out as a decimal instead of a fraction this time. And I'll go out quite a few decimal spots, whatever my calculator gives me. That is within 1/50th of the actual sum. I'll just call that of S, of the actual sum of the series. Maybe I should write approximately. By the way, 1/50th is 0.02. So this is within essentially 0.02 of the actual sum of the series. That's how we approach getting good approximations. I just write out the terms, and since it's alternating, we have this really nice pairing going on. Alternating and converging means that the terms are decreasing towards zero, so we can pair them up. And when I pair the first two terms and then terms 3 and 4, terms 5 and 6 of the remainder, we'll see if it's positive or negative. I mean, that remainder is positive or negative. And then if you pair terms 2 and 3, 4 and 5, we can see that the remainder is in absolute value, at most, the absolute value of this lead term. So it's bounded by the value of the lead term and zero. And that was the case up here as well. It's bounded by the lead term, 1 over 25, and 0. The remainder is. Let's do another example. Let's approximate this sum to within 1 over 5,000 of the actual sum of the alternating series. This alternating series, we already have established that it converges. That was one of my previous examples. -1 to the n plus 1 power over n factorial. So I know it converges. And I want to figure out what the sum is within 1/5000th of the real sum. I want to get a good approximation of that sum, and I want to approximate it to within 1/5000th. I tend to start writing out the terms in the series. If I plug in 1, I get 1 over 1. If I plug in 2, I get -1 over 2. If I plug in 3, 3 factorial is 6, so I get a +1 over 6. If I plug in a 4, I get a -1 over 24. If I plug in a 5, I get 120 up in the denominator. So a +1 over 120. If I plug in a 6, 6 factorial is 720, so I end up with -1 over 720. If I plug in a 7, I get 5040, so I get a +1 over 5040 as my term. And then if I plugged in an 8, I'd get 40,320, so I get -1 as my numerator over 40,320. I'll do maybe 2 more fractions there. Well, maybe not, maybe just 1 more. If I plug in a 9, 9 factorial is 362,880. And there we go. Make that a little bigger. Good. Now, the question asked me to approximate within 1/5000th. By the way, 1 over 5,000 is about 0.0, it's exactly 0.0002 as a decimal. The fact that it's 0.0002 as a decimal is not that big of a deal, but just wanted to point that out. That's basically approximating almost within 4 decimal places. And we look at this infinite series, which alternates, and we say the eighth term. Oh, I'm sorry, not the eighth, the seventh term. I miscounted. Seventh term is 1 over 5,040. This means that the actual sum can be represented as two parts, the sum of the first 6 terms, then the remainder. And moreover, this remainder, because of pairing the first two and pairing the second two, we can see is always going to be positive. So the remainder is always going to be positive. And also, when I pair these two terms and then pair the next two terms, I can see that my remainder is going to be at most 1 over 5,040. So it's bounded between 0 and 1 over 5,040. Now it is going to be, and by the way, 1 over 5,040 is a smaller number than 1 over 5,000. So my remainder is going to be within here. So S6 which I'm going to give an approximate decimal version of because adding these 6 terms up and then putting them in a fraction doesn't turn out to be a really nice fraction. I ended up with about 0.6319 and then a bunch of 4s. That is within 1/5,000th of the actual summation, which again, we tend to call S, but some people would write within 1/5,000th of this summation. And there we go. That's the whole thing. Now, by the way, like I said, we wanted to approximate within 1 over 5,000. 1 over 5,000 was about 0.0002. That means the actual summation is somewhere between 0.631, I'm just going to round it, 17, and 0.6321, roughly, and then a bunch of 4s. So it's somewhere between those two values, which is a pretty tight space. Actually, technically, I know that's positive, so the remainder is positive, so I can even be a little bit more precise. This is going to be S6 plus a little bit. So technically, since the remainder starts at 0, I can say it's going to be somewhere above 0.6319444444 and somewhere below 0.6321444444. that's where my summation will be. That's where this infinite sum will converge to. Most times in my class, I just ask for the approximation and then ask for the decimal version of that. So I'm asking essentially just for the S6 calculation in this case. Let's try one more of these. Let's approximate the sum of this alternating series to within 0.001 of the actual summation. Now, I do want to state that we haven't shown that this alternating series converges, but it does. The limit of 1/7 times n to the fifth does go to 0 as n goes to infinity. So it's a very easy show that this alternating series converges because of the alternating series test. Now that we know that this one converges, now we can figure out an approximation for this sum within 0.001. If you want to try this on your own, push pause on the video. All right, so we want to approximate within 0.0001, I'm sorry, 0.001. By the way, 0.001 is actually 1/1000 as a fraction. So as a decimal, 0.001 as a fraction, 1/1000. So I have that in the back of my mind because as I write out the terms in this infinite series, I'll probably write them as fractions, as I normally do. Now the first term, when I plug in 1, I get a 1 for the numerator. I'm not exactly sure why I decided, but all of the ones we've done have had n plus 1, so we always started with a positive. It's pretty obvious that if you want to, you can start with a -1 as well, sometimes if you just have -1 to the nth power. But anyways, it's perfectly fine to start with -1 to the n. Here, the first term, when I plug in 1, 7 times 1 to the fifth becomes 7. When I plug in a 2, I get a -1 in the numerator, and I get 7 times 2 to the fifth in the denominator, which is 224. When I plug in a 3, I get a 1 in the numerator, and I get 1,701 in the denominator. Now, if we want, we can stop there because 1/1701 is a smaller fraction than 1/1000, which is what I want to approximate within. I'm going to keep going just for the sake of writing a few terms, but again, we could stop right there if we wanted to. When I plug in a 4, I get 7,168 in the denominator, 7168 in the denominator, and a -1 in the numerator. When I plug in 5, I get a +1 in the numerator and 21,875 in the denominator. When I plug in 6, I get -1 in the numerator and 54,432 in the denominator. That's way more than I need if I want to approximate within 0.001. So knowing that 0.001 is what I want to approximate within, I can say the first fraction that an absolute value is less than 0.001 is this 1 over 1,701. Therefore, I think of this summation as being the sum of my first two terms plus the remainder of the summation after the first two terms. And from what I can see here, that remainder, it's going to be positive because this first term is positive. So it's going to be greater than 0. And it's going to be under 1 over 1,701. And 1 over 1701 is in fact less than 0.001 for there. So S2, which is just the sum of two terms, is going to be within 0.001 of the actual sum that I want. I'll do, once again, an approximation. I'll use the decimal version, but if you wanted to, you could have just as easily converted that to a fraction. So S2 is about 0.1383928571. That is within 0.001 of the actual summation. Move that over so it looks a little better. So essentially, I know that the actual summation is going to be, since the remainder is positive, it's going to be a little bit above that number, but it's going to be under 0.13939, blah, blah, blah. So my actual summation is somewhere between 0.138 and essentially 0.139. So this is the pattern of what we do. Whether we're using a decimal or we're using a fraction, I set up my alternating series terms. And then because of the way converging alternating series work, I can do this trick with my remainder, that my remainder is going to be bounded between 0 and the first term in the remainder. Sometimes that first term is positive, like in the last couple of examples, that first term was positive. But in the previous example, the first term of the remainder was a negative, and so we're still bounded by 0 and that first term. It just happened to be a negative. And in this case, in that case we did a couple of examples ago, we were within 1/50th of the actual summation. Then we would say my sum is somewhere between 0.8312414966. And like I said, 1/50th is about 0.02. And so we know this at most can be about 0.02 off. And we know we'd be off by a little bit under. So it's somewhere in between there, 0.83 and 0.81, essentially. So my actual sum is somewhere between about 0.81 and about 0.83. Here we went up because I knew my remainder was positive. Here I went up because I knew my remainder was positive when I was explaining it. Again, I typically just ask for what is the numerical value within 0.001 of the actual sum, or within 1/1000th of the actual sum, or within 1/50th of the actual sum, or whatever. And again, this all hinges on the remainder is between 0 and the first term that we've left off of that partial sum. So obviously I've done 3 or 4 examples, depending on if you count these as 2 different examples or the same example. So I've done 3 or 4 examples of doing approximating. If you look up in the book, there's something called the alternating series remainder theorem. And that's what we've actually been using. There's a lot of words to it, but it comes down to the idea I was mentioning earlier. If we have a convergent alternating series, which has decreasing terms, which all of ours did so far, then the absolute value of the remainder, R sub n, involved in approximating the sum by the first partial sum S sub n, is less than or equal to the first neglected term. So that would be A sub n plus 1. This is giving me a bound on my approximation, how far off my first n partial sums is from the actual summation. It's off by at most this first neglected term. Okay. By the way, this is the positive parts, so that's why we have the less than or equal to. Again, we saw in our examples, sometimes the first neglected term is negative, sometimes the first neglected term is positive. But the difference between the actual summation and the first the partial sum of the first n terms is bounded by that first neglected term and 0, obviously. So if we want to do approximations with alternating series, this is really, really nice. One thing I want to mention, in these previous examples, it took us a sum of the first 4 terms to approximate within 1/25th. In this scenario, it took us like 7 terms, the partial sum of the first 7 terms, to approximate within 1/50th here. To approximate within 1/5000th, what we did is the first 6 terms here. And to approximate within 1/1000th, we took the first 2 terms here. So what I'm saying is that in some alternating series, you can get to some really, really low values quickly. And in other alternating series, it might take you a while to get really good approximations within like 0.001. So sometimes we would like to determine maybe not what the sum is, but how long it would take to get within that 0.001. So for instance, if we took our original alternating series and we ask how long would it take for this, how many terms would I need? What partial sum would I need so that I could approximate within 0.001 in this alternating series? It would be different. It would definitely not be within 2 terms like it was here. But we could figure that out by this alternating series remainder theorem and the concept of the first neglected term. So I want to approximate within 0.001 or 1/1000th for this series. And I'm saying, how many terms do I need? I'm not going to actually do the approximation because we'll see in a second, it's going to take quite a few terms. All right, so how many terms do I need? Or in other words, what n should I use when computing the S sub n that I'm looking for? All right, all I have to do is take the terms and ask when in absolute value does this get under, or does this hit or get under the 0.001. So when does this the absolute value of this, obviously some of these things can be negative, so when does the absolute value of this get under or hit 0.001? We've taken absolute value a lot, so that's what we get. If I multiply both sides by n squared and then divide by 0.001, I'm multiplying by positives and dividing by positives, so the sign doesn't change. 1 divided by 0.001 has to be less than or equal to n squared. And then I would take a square root of both sides. If I take the square root of 1 divided by 0.001, since everything's positive, the sign will remain the same. I get 31.62 roughly. So that means I need to go out 31 terms. I need to use basically S sub 31 and then S sub 32, or excuse me, the 32nd term will be smaller than 0.001. Let's check that out. Let's confirm that. Take 1 over 32. Take 1 over 31 and square it. And then compare it to 1 over 32 when you square that. All right. If I square 31, I get 961. So I get 1 over 961. That's not quite big enough for my remainder, but 1 over 32 squared is 1024. That is 1 over 1024. So basically, what you're going to do is you're going to let this 32nd term be your remainder, and you're going to use the first, they're going to use the partial sum of the first 31 terms. Hopefully that makes sense. So all of this was just computing what we needed, and this is the confirmation that that is the cutoff between those. So we'd be using S sub 31 as my approximation. And then if we did that, then the remainder in absolute value, the remainder after 31 terms, we know would be less than or equal to 1 over 1024, which is less than 1 over 1,000. So the 32nd term is the first neglected term, if that makes sense. So this is all we need to do in order to figure out how many terms to use. Now, obviously, I wouldn't do this by hand, summing up the first 31 terms. That would take a really long time. But for a computer, it's pretty quick to add up 31 terms. It's pretty easy to do that. And we can get a good approximation for this sum after adding up just 31 of those terms. All right, so it would take 31 terms for this thing to have an approximation within 0.001. And we saw again in the previous examples that this one, it would only take 2 terms to approximate within 0.001. In this one, it wouldn't take very many terms either, and that's the one we actually used. So this shows that a couple of really nice things come with alternating series. One is we have a really nice test for convergence. As long as the terms are going towards 0, the positive component of the terms are going towards 0 and decreasing. So if the limit is 0 and the terms are decreasing, the positive components are decreasing, then we have a really nice, then we know our alternating series converges. So that's a really nice test for alternating. The other big benefit is, as we can see, we get really good ways to approximate with alternating series. And we have some bounds on how big of our error is going to be. We don't get those bounds if the series is not alternating. If the series is not alternating, then it's tougher to get bounds on my remainder. So this is the end of this section. Hopefully, we learned something about alternating series, the test for convergence, the idea of absolute versus conditional convergence, and then good approximations.